So in the Big Data Analytics project, we're really looking at how to build algorithms and design algorithms that make the processing of big data more efficient. This is really important. We have so many services inside Microsoft, such as Bing and some of the new services that are appearing in Azure, that are underpinned by processing of big data. Building algorithms that let us do this more efficiently, either using less hardware or being faster, is really important in order to allow us to process this big data in the future. And in particular, the project that you're going to hear about today, Fennel, has been looking at how you would lay out graphs across a cluster of machines.
Our research focuses on designing novel algorithms and systems for efficient processing of big data. This is a research area that requires a diverse knowledge, including foundations of algorithms, databases, and systems. So the driving force of our research is to empower the society to perform big data analytics that was previously beyond our reach, or it was performed in an efficient way. So to date, big data analytics has been standardly deployed by large organizations such as online services providers, for example for web search or online computer games, financial institutions such as banks, and retail and online retail. So it is believed that making big data analytics accessible more widely to enterprises, small and big companies, governments and health organizations will have significant benefits on our society as a whole. So for example, one of the computational challenges is to efficiently perform streaming computations. So streaming computation is about performing something like this. Think of a massive stream of data that arrives into a system, and we want to perform a computation on it. This might be a PC with limited memory, so we can't afford storing this massive stream into memory, but we need to compute on the fly. So what we need is efficient algorithms to compute while actually using a budget memory. Now, this picture becomes quite different when we move into a distributed system machines, say in a data center of tens of thousands of machines. In that setting, we are going to have a number of machines, and data is going to be partitioned in some way across. Either these machines, they have local access to data, or this data arrives in a real-time fashion to the machines. So what we are going to do now, we want to perform a computation of a kind on this, and there's going to be a designated machine which orchestrates the entire computation. At the end, it should report the answer, the solution to the given problem. Now, in this given picture, in addition to time and space complexity, there's also issue with designing efficient algorithms with respect to the communication complexity. So we really care about how much of information is exchanged between these computational units in the system.
So the idea here is, if you're a Facebook or a LinkedIn and you've got a very large graph, you would like to get it such that the vertexes inside the graph are co-located on the same server. And you would like algorithms that will very efficiently partition the graph to get this locality. And Fennel has been looking at algorithms that will allow this to be done online rather than offline, which is currently the way that many of the algorithms work.
So these input graphs can be of massive scale. For example, if we talk about web graphs, this is going to be in the order of tera URLs. So we developed a framework for graph partitioning, which is based on optimizing an objective function. So in my view, this technology is based on a nice blend of a novel algorithm design with a practical system implementation of it.